Alright, welcome back, Physics Fiends. Today we have text problem 8-55, one of the suggested problems for lesson 21. Alright, as always, please get out a blank piece of paper, scratch paper, or a blank printout of this problem so that you can follow along with me as I will be pausing throughout the video to ask you to carry forward a few steps to see where you're at in understanding the concepts in this problem, which we will investigate right now during our read step. So as we read through this problem, we see that we have our mass here, and we have a value for our spring constant, and it looks like we have a displacement of the spring, and we have some friction involved. So as this block has some initial kinetic energy, and it compresses this spring, you can guess that we probably have a conservation of energy type of problem. So that's what we'll put here. That's my laser pointer. We have conservation of energy. Part A wants us to find out the work done by the spring force, so we have some work at play. We've got friction, and looks like we may have to do some work with Newton's second law, just dealing with that friction force. So we'll throw that in there and see if we use it. Maybe we do, maybe we don't, but at least we're ready to tackle it if need be. Alright, so as we proceed from our read step, we have our draw step, and for the most part we see everything that we need for this problem. We can say that we have some initial speed here. Of course, with our beautiful blurry lines, we can see that this block is in fact moving initially before it interacts with the spring. And we can say that maybe perhaps that our block compresses the spring some amount delta x. Alright, so as we move on to our givens, I've listed them out already, but we have our mass, our spring constant, our spring displacement from equilibrium, and our coefficient of kinetic friction. Alright, as we look at our assumptions, if you remember from last time when we were talking about potential energy, and we had our roller coaster starting at some height h, and it went down and up and then down, we assumed that there were no non-conservative forces at play. That's because we expected the potential energy to convert to kinetic energy and convert entirely back to potential energy once it reached the original height again. But again, with the importance of the read step, we see that we do have friction in this problem. And if we have friction, we know it's a non-conservative force, because no matter which direction you go, you will have some type of negative work done. We'll get more into that once we push through the problem, but the only assumption I can really make at this point is that we have a closed and isolated system, in the sense that any energy that is put into our block or out of our block is contained inside of our system. Nothing escapes, so that we can say we can in fact conserve energy. Next, we want to look at what we're being asked to accomplish in this problem. So our first task is to calculate the work done by the spring force. So I have large W for work and subscript S for the spring. Next, we need to calculate the increase in thermal energy as the block slides along the floor and compresses the spring. And then finally, we need to calculate the initial speed just before the block makes contact with the plate connected to the spring. Alright, our next step is the physics step. So, based off of our reading and what type of problem we expect this to be, this is your opportunity to pause the video, write down the pertinent physics equations that you will need to solve this problem, and once you're finished with that, resume the video and you can compare what you put to what I put and see where you're at. Alright, so how'd you do? Well, like I said, we have our conservation of energy here, and this can be further simplified into our work non-conservative is equal to our change in mechanical energy. We also have our Newton's second law equation, and we have our first force due to kinetic friction. Let me quick run over these. The first equation, here we have the change in thermal energy plus the change in mechanical energy, that's an M, and we have added to that the change in internal energy, and that's all equal to 0. Remember, if we have a change in something and we want to conserve energy, then all of our changes here need to add up to 0. We don't have any energy leaving our closed and isolated system. Alright, so we made that assumption. This is the equation to back it up. Alright, so let's move on to our solve step for part A. Alright, so as we begin to solve, part A asks for the work done by the spring force. Well, we have our work done by the spring force. Let's see. Oh, we missed an equation in our physics step, and that is our relationship between our change in potential energy is equal to the negative work done by a force. So if we rearrange the equation I just wrote here, we can go back and say that the work done by our spring force is the negative change in potential energy. Well, of course, if we're looking at a spring, then we're looking at the potential energy due to the spring force. So let's continue with this. We know from our PRC that our equation I can't talk and write. Our equation for the change in anything is always final minus initial. So as we look at our situation, in the final frame, we have the block compressing the spring. So what is the potential energy of our spring? This is where you respond with the equation, or write it down on your scratch piece of paper. It is 1/2 k x squared, where k is our spring constant and x is our displacement from equilibrium. And what about our initial potential energy? As we look at our drawing here, is the spring displaced at all? No, it's sitting at equilibrium. So if we don't have any displacement from equilibrium, what's our potential energy? 0. Good. Okay, so in order to calculate the work done by our spring force, we have to look at our change in potential energy, which we have listed here. So our work done by the spring force is equal to negative 1/2 k x squared. Let's see, looking at our givens, we have our spring constant and we have our displacement from equilibrium. So as we calculate this, we get negative 0.90 joules. Now, why is it negative, you might ask? Remember, if the displacement vector and the force vector are in opposite directions, i.e. 180 degrees apart from each other, then we will have a negative sign in front. Now remember, the spring force is a variable force. We can't use the work is equal to the force vector dotted with the displacement vector. That's only for a constant force. Here we have a variable one. We would have to do the integral to work through that. But we already did last class, which gave us this result right here. So our work is complete. And it's just a matter of inputting the correct variables into our equation. But at the very least, for part A, the check step does agree with our understanding of the work done by our spring force. All right, part B. Part B asks us to calculate the increase in thermal energy of the block floor system. So, of course, this is where the fun starts to begin. So, if we're going to conserve energy here, because we want to find the increase in thermal energy, we look at our conservation of energy equation, which we listed out in our physics step. Okay, so we have our three energy terms that we'll be working with. We have our change in thermal energy, which is our objective for this part, our task. We have our change in mechanical energy, and we have our change in internal energy. For this course, we are going to assume that our change in internal energy is always going to be zero. It's things like, all right, we have a radioactive block, and so it's actually giving off heat. Lots of internal processes that might be occurring inside our body or inside our system that we just don't want to complicate things with, because they are generally complex type of energy processes at play. So if we're just working with our thermal energy and our mechanical energy, then we can work with this. So as we do our equation here, we have our change in thermal energy is equal to the negative change in our mechanical energy. Well, we know from our PRC that the change in mechanical energy is equal to the non-conservative work done. So here's our equation that I'm referring to. Our work non-conservative, or the work done by non-conservative forces, is equal to the change in mechanical energy. Well, if these two items right here is our change in mechanical energy here, then we can substitute in, and we find that our change in thermal energy is equal to the negative work done by our non-conservative force. And what non-conservative force do we have at play? Drum roll, please. The kinetic friction force. Good. So our force due to kinetic friction is our coefficient of kinetic friction times the normal force. And if we assume that our kinetic friction force is constant, then we have the work done by our non-conservative force, which is friction, is equal to our force vector dotted with our displacement vector. Well, it's not as easy to just plop our kinetic friction force into our work equation because we don't know what the normal force is. Well, what can we do if we have a horizontal force that has some component with the vertical aspect in it? Well, we can do Newton's second law. So I want you to pause the video. I want you to do a Newton's second law analysis on our block here. I want you to get to the point where your Newton's second law has all your forces in the proper directions and equal to your mass of the block times its acceleration. Alright, welcome back. So here's our free body diagram. The forces acting on this block, we have our weight force that is anchored at the center of mass pointing down. We have our normal force, which is anchored at the surface pointing up. We have the force due to the spring on the surface in contact with our little panel here. That's pointing to the left. And we have our force due to kinetic friction also pointing to the left. Now go ahead and pause the video again and go through your Newton's second law analysis in the x and y direction. Alright, welcome back. So hopefully you have your Newton's second law looking like this. We have our x direction here, and so we see that based on my coordinate axes, the kinetic friction force is pointed in the negative x direction, and the spring force is also pointed in the negative x direction. And I'm not really sure what the acceleration of our block in the x direction is, so I can't really proceed any further on this aspect of our Newton's second law analysis. But in the y direction, we only have two forces at play. We have our normal force, which is pointing up, and our weight force pointing down. Our block isn't jumping up off of the surface, so the acceleration is 0. And so our normal force is equal to our weight force. And really, that's the most important part of our Newton's second law analysis, because really what we need is that normal force. So we really didn't need to do the x direction, but it's always good practice. So as I make my substitution of my normal force into my kinetic friction force, I have the kinetic friction force is equal to our coefficient of kinetic friction times our weight force, or the mass times the acceleration due to gravity. Now I can substitute this into my work due to non-conservative forces, or in this case it's just the work due to a constant force. Now before I put it in, I want you all to pause the video again. I want you to put in our equation here into our dot product operation and go through the process of getting an algebraic solution for the work done by our kinetic friction force. Okay, so this is what I have for the work due to our non-conservative force. And if we break this down into magnitude and angle form, then we have our kinetic friction force magnitude times the magnitude of our displacement times the cosine of the angle between our vectors. So what is the angle between our vectors here? Well, we have our d vector pointed, the displacement vector pointed in the positive x direction, and our kinetic friction force, which doesn't have a vector hat, but now it does, is pointed in the negative x direction. So if they're parallel but pointing in opposite directions, then the angle is 180 degrees, and the cosine of 180 degrees is -1. So the work done by our non-conservative force is negative times the coefficient of kinetic friction times the mass times the acceleration due to gravity times our displacement, which in this case is 7.5 centimeters, times cosine of 180, but that's where that negative sign comes into play. So that's the work done by our friction force. This equation is now going to go into our change in thermal energy equation. And I'm going to go to the next slide so I have more room, and we'll continue from there. Alright, now that I have a little more space, we have our change in thermal energy is equal to the negative work done by our non-conservative force. And we determine through our conservation of energy and our Newton's second law analysis that the work done by the kinetic friction force is listed as such. So as I substitute these two equations into each other, I have the change in thermal energy equal to negative times the negative times the coefficient of kinetic friction times the mass times the acceleration due to gravity times our displacement, and that comes out to 0.46 joules. Now let's go through the check process. I have a block that is traversing over a rough surface. That tells us from our personal experience that friction is going to increase heat. And so initially it's traveling, and as it hits that friction surface, it begins to generate heat. And if it's generating heat, then my final value for the thermal energy will be higher than my initial value. So I should have a positive value, which I do. Now I want you to remember that this change in thermal energy is from this point where the block makes contact with the spring to the point where the spring is fully compressed at 7.5 centimeters. So we're not looking at where the block is way over here. We're only looking at the point just before it touches the plate here to the point where it is fully compressed at 7.5 centimeters. So that's what this value actually means. It's the heat generated from our point of equilibrium to the compression point of 7.5 centimeters. Alright, on to part B. Now I want you to pause the video again. I want you to generate your conservation of energy table that is outlined in our course supplement, and you may have seen it on some of the other suggested problem solutions. So pause the video, draw out your table, and we'll go from there. Alright, so we have our conservation of energy table here, and I'll go through the components here. We have our final mechanical energy, our initial mechanical energy, and the work done by non-conservative forces. So, of our mechanical energy components, we could have a translational kinetic energy in the final or the initial frame. We could have rotational kinetic energy. We're not there yet, so that's going to stay blank for this one. We have the potential energy due to the gravitational force. And we could have the potential energy of our spring force. So as we lay this out, I want you to pause the video again, fill out the table, and we'll continue from there. Okay, so this is what your table should look like. Initially, just before the block impacts our little panel connected to the spring here, we have some translational kinetic energy. There's nothing, no other mechanical energy term on the initial side, which is why I have 0 for the rotational kinetic energy. I can assume that my gravitational potential energy is 0 if I say that at this height it's 0, and since there's no change in height, I have zeros across the board. And then for our spring potential energy, initially we don't have anything. But as we look at our final frame, our block has hit a point where the spring is fully compressed. It no longer has any translational kinetic energy. It's right at that turning point where the block's about to change direction and be pushed back out. So at this point, it doesn't have any speed, it's not moving. For that instant in time, it is motionless. Same with the rotation. Again, no change in the gravitational potential energy, so we can hit that to 0. But now, we do have a spring potential energy. So at this point, we can work with our spring potential energy, and we can work with our kinetic energy. But let's not forget, we do have friction at play here. So we do have some non-conservative forces doing work. I'll move to the next slide and lay it all out. Just kidding, I think we have room here. Go ahead and pause the video. I want you to write this out with the terms in our table. Alright, welcome back. So here is our conservation of energy equation. So we have our non-conservative work, which we worked on the last slide. We can put that directly into the work due to non-conservative forces. That's all equal to our final mechanical energy, which is only our spring potential energy, minus our initial mechanical energy, which is only our translational kinetic energy. Everything else is 0. And so here is our equation to work with. What are we searching for? Well, in part C, we're looking for the block's speed just as it reaches the spring. So this is what we're looking for right here. we can do some algebra to rearrange this and solve for our objective variable. Alright, so here's where we're at. We did our table here. We have our carryover of our work due to non-conservative forces. And as I flesh out my table into our equation here, I have my work done by the kinetic friction force. I have my final mechanical energy minus my initial mechanical energy. So again, our task is to calculate that. So of course, to do an algebraic solution, we need to isolate it. So I'm going to switch these two, or better yet, why don't you pause the video and take a stab at it yourself, and once you're done with that, resume the video and check against my answer. Alright, so welcome back. Hopefully you got the answer that I got. So I moved this over there and that over there, and once I did that, then I divided both sides by my variables in front here. I was able to cancel out the 2 with this term, which is why it's not there, and it should be over here. And I was able to cancel out the mass term on the second one, which gives me what I have here, but I am dealing with the speed squared, so I take the square root of both sides and I get that. Now, once I have my algebraic solution, all I need to do is input my given values. I was given the spring constant, my spring displacement, the mass, the coefficient due to kinetic friction. I already know my acceleration due to gravity, and again, d is my displacement in this aspect. We'll go ahead and be consistent. I can't. Okay, well, we can always rewrite it. Kx squared over m plus 2 mu sub k g times x, where x is our displacement, and it's just me replacing that right there. Once I've done that, the speed is 1.0 meters per second. Again, two significant figures. My units are meters per second, and this is the speed directly before it makes contact with that plate. So it may be that over here it has a much faster velocity because it's slowing down all the way to this point, but really what we're looking at is the interaction between the block and the spring from equilibrium to 7.5 centimeters. Alright, so let's review. We had a chance to go through conservation of energy. Then we got a chance to go through our conservation of energy table. We did some work calculations, and we got a chance to bring back Newton's second law. So a lot of concepts involved in this problem. Hopefully you didn't get too bogged down with the back and forth of concepts, but I will stress the importance of this conservation of energy table. Again, we give you tools to simplify the process and help you think about the problem and less about did I remember this potential energy and this kinetic energy, so on and so forth. It lays it all out for you. You can reference back to it as you go from part A to part B to part C, or however many parts are in a problem. Alright, so that's all I have for this problem. I will see you in class tomorrow.